Thanks everyone for coming. It's my great pleasure to have Todd Coleman here today. I've known Todd for a very long time. I think we met at a conference in Sweden and had a very lovely time there. Todd has certainly won many awards, and he's a fellow of various things, and we're certainly excited to have him here today. Actually two quick stories about Todd. One thing that I sort of admire about him so much is that he has a very deep understanding of mathematics, but he's really interested in also applying that mathematics to a wide variety of areas. And I think you'll see today the amazing sort of breadth of the things that he's interested in. A slight sort of funnier story is that his favorite book, like mine, is called The ABCs of Mathematics. And ironically, he sent me a picture of his favorite letter in the book, and it's called J, it's after me. And it says, J is for joint probability. And he sent this to me as he and I both were reading our sons this lovely book. And so without further ado, Todd.
Thanks, Jamal, for the introduction. I had a great time interacting with the students and postdocs at lunch today. That was a lot of fun. And so I'll start by telling you a little bit about myself. So I did undergraduate studies at the University of Michigan, go blue, just like Aaron Ryder studied in the back. And did graduate studies at MIT in applied probability and information theory. And my graduate advisor gave me some of the best pieces of advice in my career, where she strongly encouraged me to not just take a faculty position in electrical engineering right away, but to delay my start date and do a postdoc in something wildly different. And so I ended up doing a postdoctoral study also in Boston with a gentleman named Emory Brown, who is a MD, Ph.D. practicing anesthesiologist. What's also interesting about him, though, is that he has a Ph.D. in statistics. So it allowed me to learn physiology through the language of probability, especially given the last time I had taken a biology course was AP biology in high school. So I began to learn the language of physiology and neuroscience through statistics and probability, and I began to work at that intersection and also to do some technology development in the process. So that's a little bit about my story. And so why am I here talking to the camp folks? I'm here talking to the camp people to study or to think about the problem that's simplified by this picture. And the high-level idea is, suppose that I have this Plinko board. I don't know if people are familiar with this, but basically what happens is I have these balls that are sitting on top, and you can imagine they come from some distribution, like a uniform distribution. And what I would like to do is I would ultimately like the shape of those balls to represent something here, almost like a Gaussian. And the question I'm after is, how can I engineer this board so that these balls sort of randomly drop through here, then the ultimate shape is here. So this is slightly different than how we typically think, but I'm really interested in the transformation in doing that. And if I can solve these problems, I can address problems in a variety of domains, such as Bayesian Inference, something called Domain Adaptation, and then Generative Modeling. So if we think about Bayesian Inference for a second, here's this quote from Michael Jordan. And he said, I think that data analysis can deliver inference at certain levels of quality, but we have to be clear about what levels of quality. We have to put error bars around our predictions. And at a high level, what he's saying is that a lot of machine learning problems boil down to solving some type of estimation algorithm that's finding a point estimate. And so if we take a look at these two curves right here, we notice that the location of that red dot maximizes both the blue curve and the green curve. But we know that the blue curve has less uncertainty than the green curve. So how can we capture that uncertainty and not just our best guess? And so as some of us may know, this wasn't Michael Jordan, the basketball player, but a statistician at UC Berkeley, just to make sure no one fell asleep right away. So what I would like to do is to be able to capture the curvature or other information about how the blue and the green separate each other from one another. And this is important in some applications where, in some sense, what I would like to do, if we think about Bayesian inference and Bayes risk and whatnot, one of the purposes of Bayesian inference is that I have this latent variable x and I take a measurement y, and there's some decision or action that I need to take, and I want to find the action that minimizes an expected loss given the information that I have. And so if we take a look at this conditional expectation on the expected loss of that action that also operates on my latent variable, well, suppose that I could draw IID samples from the posterior. Then I can approximate that expectation by just that sum right here, and I can find optimal decision very quickly. And so, as we all know, trying to generate IID samples from the posterior is not always easy. It's typically done with something called Markov chain Monte Carlo, but let's just imagine for a moment that we could do that. Then at a high level, what I could envision doing is, suppose I can sample easily from the prior, could I build a transformation that will transform those into samples from the posterior? I generate IID samples from the prior, shove them through this transformation, now I have IID samples from the posterior. That's the high level idea. So so P is the prior and Q is the posterior, keeping in mind also for Bayesian inference in many situations, I only know the posterior density up to a normalization constant. Can I do this in a manner where I only know Q up to a normalization constant? Another example of this is something called domain adaptation that some of you may or may not be aware of. And the high level idea is that suppose that I built an algorithm and I can train it very well on a certain type of data set. So for example, if I see these pluses and these circles right here, and I can build a very nice classifier for this, what happens now if I have a data set where in some sense it's not exactly like those pluses and the circles, it's now this gray type of data set? Is there some type of approach where I can basically transform what occurred before to the previous setting, and then I can perform my classification algorithm? So if I can basically transform the domain to a domain where I've already performed a good classification engine, then I can borrow the previous type of classifier as done before. And then the last application of this can be within the context of generative modeling. And so a high level idea, and this relates to Gans and deep learning that some of you may be familiar with, is that if I have a whole bunch of random images of cats, the high level idea is, suppose as an intermediate step, I can learn a transformation that transforms these independent, identically distributed samples of cats into samples from just a standard normal Gaussian distribution. Because if I can do that, and I can do that well, I can then generate new samples from a standard normal Gaussian distribution. And suppose this map has an inverse, I can now generate new images of cats. And so this is then allowed me to build a generative model. So these are the types of questions that we're interested in. So if we take a look at the framework that captures those examples, the high level idea, just like in the Gans setting, is that I might not know P exactly, I might only have samples from it. And suppose that Q also has a density, but I only know it up to a normalization constant. And this captures the Bayesian inference problem. And the high level idea is with those samples, can I transform samples from P to Q? And it turns out we'll make this assumption of log concavity on Q, and you'll see why in a moment. And so how do we think about this problem? Well, the way we think about this problem, first of all, is that, so one of the things that's well known in the optimal transport literature is that if P and Q are both densities in the d-dimensional Euclidean space, so in the same space, if they both have densities, then it's well known that there always exists a map that transforms P to Q that has a certain amount of structure. In particular, it can be a diffeomorphism. There always exists a diffeomorphism whose Jacobian is positive definite. And so this is a famous result of optimal transport theory by Brenier. And so what I'm going to do is I'm going to constrain myself to that set of maps. So maps with some structure, diffeomorphisms that are basically monotonic, they're quote unquote increasing, positive definite Jacobian. Now one thing I benefit from that is that if I'm working with such maps, then one of the things that we can remember is that, remember the distribution Q has a density. Suppose I take Q and I look at the right hand side of this equation right here, I just invoke S of U times the determinant of the Jacobian. Well, that actually defines a density, right? This is nothing but the Jacobian equation for densities. So for any possible such diffeomorphism, this defines some density that's parameterized by S. Now keep in mind, so what I'm saying is that map S is linking some density to Q. But that density need not be the true P that the samples came from. But the nice thing about this is I can now imagine some optimization algorithm where I was originally searching over S's and now I have an objective function. And the objective function can be some type of distance between the density induced by us and the target density of interest. And so one way we could think about this is, and it turns out, one way you could think about this is basically the principle of maximum likelihood estimation. So if I have I and D samples, and I assume that they come from some parametric class of densities, if we take a look at what maximum likelihood estimation is doing, we know it's maximizing the probability of the data, minimizing the negative log probability of the data. This is an empirical sum, so this is an empirical estimation. For large n, I can approximate that as the expectation with respect to the true p. So if this is the minimizer, I can always add some constant. And so what if I add the constant of the expected value of log p of the data right here, then lo and behold, this becomes a relative entropy. So the high-level idea of using the distance measure of being the relative entropy between p and the p-utility that was induced by the map is not at all abnormal. In fact, this is really what maximum likelihood estimation is doing. So I could envision a maximum likelihood estimation problem as follows, which are where I'm basically just borrowing from the previous slide, where I take a look at this relative entropy between p and the 2p and the p-utility, and I do exactly as I did right here. So this is the expectation with respect to the true p, but now instead I use the empirical expectation. The nice thing about this is that now this is using the samples from x1 to xn. And so this could be a natural way to think about this. That's the good news, but the bad news is to keep in mind is that if p and q are very different, then that map S is going to be, can be arbitrarily sort of nonlinear. And so trying to do this in one fell swoop might be very complicated, and how am I going to parameterize these maps to perform this estimation procedure is not at all obvious. So the high-level idea that we got interested in is kind of like if I'm going to find the minimizer of a function, and I started an arbitrary initial condition, one way I can go there is via something like gradient descent. So if we stand back and we think about gradient descent, I know that if the gradient is positive, I move in one direction. If the gradient is negative, I move in the opposite direction until I find the point where the derivative is 0. And we know that it can be described with this very simple equation right here, where wk plus 1 is wk minus some tau times the gradient of the function. And notice one thing I'm doing right here, and some of us may remember this from our numerical analysis class, is I evaluate at wk plus 1, right, rather than at wk. And if we remember, this implicit scheme, gives us some stability. One nice thing about the implicit scheme also, is, if you may remember, is that there's another simple way to describe this in a variational sense. So this is basically just a minimizer of this quadratic plus tau operating on the objective function. And the way to see this very simply is, if I take a look at this function and just set the derivative to 0 with respect to w, then I get basically w minus wk plus tau evaluated at j. And then if I move wk to the left-hand side and I subtract tau, then I get exactly this equation right here. So if I operate in continuous time, and then this is just w prime is negative the gradient of j, and we know that if j is well behaved, namely if it's convex, then I know that w across time is going to converge to its minimizer. So this is sort of well known, and so it turns out that what may not be as well known to everyone here is that there's an analogous statement about gradient flows where now w's are not points in d-dimensional Euclidean space, but now I have over the space of probability measures. So let's imagine now that my decision variable is probability measures, and the high-level idea is as follows. Suppose that ultimately I have an arbitrary distribution, p, and I'm trying to imagine a continuous time evolution of these distributions that they're then evolving towards my target q. And so q is almost like the minimizer of some type of objective function, and p is kind of like the initial condition where I started with gradient descent. So it turns out that there's a well-behaved equation in statistical physics that describes evolution of densities. It's called the Fulcrum equation. Some of us may or not be familiar with non-equilibrium thermodynamics. So if I start a system not in equilibrium, it's going to converge towards its given distribution. What is the exact trajectory of how that occurs? The heat equation is a special case of this, by the way. So it's given by this equation right here. Now here's what's not at all obvious. It turns out that evolution, if I were to discretize time, is basically operating exactly as a gradient descent. And what I'm showing you right here is I can say is that the distribution at time step k plus 1 is the minimizer of a quadratic of a distance between where it was previously plus tau operating on some objective function. And this objective function is just a relative entropy between rho and the target distribution. And notice that this kind of makes sense because this thing is non-negative, and ideally it should decay as it evolves, and it eventually should become zero. So what was remarkable is that it was shown in this beautiful paper by these mathematicians that this is exactly the evolution of the Fulcrum equation. So it's called the variational formulation of the Fulcrum equation. As a side note, notice that the relative entropy, if I fix Q, the relative entropy between rho and Q is definitely convex in rho, as a side note. Jensen's inequality. Yes, sir?
Sorry, your flux, capital psi, what is it in this case?
Say it again?
Your flux, capital psi.
Oh, I didn't, oh, my apologies for not being clear here. So suppose that I represent Q as a Gibbs measure. So it's just e to the minus beta times psi over a normalization constant. That's exactly what that is. So this encodes the energy function associated with Q. Yeah. So this is standard stuff, statistical physics, the Fulcrum equation. But what's not obvious is that the evolution of the densities obeys this. And the most important thing I didn't say is what distance measure between probability measures is used. And it turns out that it's the L2 Wasserstein distance. So the Wasserstein distance from optimal transport theory basically is this expected value of x minus y, L2 norm squared. It's the minimum over all such expected values over joint distributions for which x is from rho and y is from rho total. So this is the standard L2 Wasserstein distance. Okay, so one other nice property about all this stuff is if you use this sort of continuous evolution of densities is that, so here I'm representing Q as a Gibbs measure, so that goes to your previous question. So if I take a look at the energy function, if the energy function is well behaved, basically means that the energy function is not only convex but strongly convex, then it turns out that this evolution of the relative entropy, it decays exponentially fast, okay? And so for example, if Q is a Gaussian, then it obeys this with lambda equals 1 because the second derivative of 1/2 x squared is 1. Okay, and so this was proven in another paper with thousands of citations in the math community. And so what I was interested in doing is leveraging, remember the high level idea is rather than just trying to build one map all at once that pushes P to Q, maybe I could imagine this sequential evolution of maps. So I compose one map, so that what these maps are doing is they're pushing these so they're evolving according to the Fulcrum equation. So in some sense what I want to do is I want to go from evolution of distributions to evolution of maps, and then I can compose these together. And so one of the things that we know for sure is that if we take a look at this, this objective function, which is the distance between rho at time step k minus 1 and my decision variable rho plus tau times the relative entropy, then one of the things that we can note is that for any decision variable rho that I pick, there's some underlying S map that's pushing the rho k minus 1 distribution to that rho. Is that clear to everyone, right? If I have rho k minus 1 right here, for an arbitrary rho, there's some map that's transforming samples from this to that. And that's the S that I'm talking about right here. Okay? And so this is the Wasserstein distance between the distribution induced by this. But now suppose I just took a look at this quadratic expectation. So remember the Wasserstein distance is the infimum over all such maps of this quadratic. So I have this inequality right here. So and then further, again, wherever I see rho, I can use S push forward rho k minus 1. So if I have a rho k minus 1 for an arbitrary rho, there's an underlying S. And that S lies in the space of monotonic diffeomorphisms. Now what we can also show without too much work, and again this goes back to Brenner's theorem, what I can show is that when I'm solving this variational statement, which comes from that paper in the math community, now suppose that I solve this variational question, but now this is over the space of maps. So I'm searching over the space of maps. And it turns out that this minimizer has the property that is transforming rho k minus 1 to rho k. Okay? And so this is nice. And so in some sense that evolution of the densities underneath there is an evolution of maps. And so we can stand back and look at this optimization problem a little bit more. And if we remember, this is our beloved Jacobian equation right here. And so our argument is that if the Q distribution is log concave, then this is actually a well-behaved convex optimization problem. And the proof of this is is pretty simple. And so notice that this is clearly quadratic in S. So that's very well behaved. So if I stand back and I take a look at this relative entropy, the first thing that I'm going to do is as follows. So remember, the relative entropy is invariant to invertible transformations. So what I can do is, so right now I have S pushing forward a rho k minus 1. Let me put S inverse push forward on the left and S inverse push forward on the right. That's an invertible transformation because it's a diffeomorphism, so the relative entropy does not change. And so I have this statement right here. Now if I stand back and I take a look at S inverse pushing forward on Q, so think about this. S, the way I describe this distribution right here, is such that when it gets pushed forward through S, it goes to Q. So equivalently, if I take S inverse and I start at Q, then I end up here. And so that's exactly what I'm saying right here. That's this distribution, which obeys the Jacobian equation. So now when I stand back, and it's nice when I write it this way, because notice rho k minus 1 is not a decision variable. So this is just an expected value with respect to rho k minus 1. And now I can write out this density, and remember it's a product of Q times the determinant of a Jacobian. When I take the negative log of both of these, things are nice. So remember, my assumption is Q is log concave, which means its negative log is convex. So this term is convex in S. And then secondly, let's remember, so remember the space of maps is the space of maps whose Jacobian is positive definite. Remember the log det operator is concave over the space of positive definite matrices. So the negative of that is convex. So so this whole sum is a sum of convex functions. So it's convex in S. So that's kind of nice. So then the next step that we went to is we said, well, there's a couple of things to remember. Another reason that I deliberately wrote it in this other way where I did the push forward on S inverse is because notice that there's a sum of two expectations. When I write it the way I did, now both of them are expectations with respect to rho k minus 1. And remember, rho k minus 1 is not a decision variable, and further I can have samples from rho k minus 1. Okay, so now I can replace this expected value with rho k minus 1 with just a normalized sum of IAD samples, x1 to xn, that are drawn from rho k minus 1. Okay, and so I just get this expression right here. So this allows me to now think about only having samples. And then secondly, how am I searching over a space of maps, right? That appears to be complicated. Space of monotonic diffeomorphisms. Is there some finite dimensional way that I can do this, right? Where maybe in the limit I can approach the space of all maps. And it turns out log concavity helps us there too. So for starters, what I can do is I can build this matrix B, okay? And so B has B is this, it has number of rows equal to the number of dimensions in X, and it has M columns. And suppose I do the following. I just let S of X be X plus a sum of nonlinear functions. And keep in mind, you guys, because we're doing almost this continuous time evolution, what that means is going from time t to time t plus tau, that map is almost the identity function. It's slightly nonlinear, right? And so this is the identity, and now this is sort of that leftover nonlinearity part. And the way I can parameterize this map, perhaps, is to use maybe some type of almost Fourier-like basis, but somehow taking into consideration the fact that we're dealing with distributions. And so there's a nature of the polynomial chaos that Norbert Wiener came up with, and these are basically a set of orthogonal polynomials with respect to a probability distribution. And so what I mean by that is I can define an inner product, but it's with respect to a probability distribution. And so what I'm doing is I can use the polynomial chaos with respect to Q as an example, since I know the structure of Q in many situations. And so those can be these nonlinear functions phi n that I use. I'm just using a weighted combination of them. So one nice thing about log concavity of Q is that it implies sub-exponential tails, and this tells us that the polynomial chaos is actually dense in L2 of P. So basically the space of all possible maps can be represented in a Fourier sense using this polynomial chaos. So with that, the last step that we wanted to do is we wanted to solve this optimization problem, but we wanted to do it in a way that's computationally efficient. And so if you stand back and you look at this problem right here, notice that I have a sum, I going from 1 to n, and each one of these terms has xi, and it also has that same s. So that same s is in each of those terms. keep in mind, if those were S1, S2 in each of those, then this would be a completely separable optimization problem. So can I somehow use some of these principles from alternating direction method of multipliers so I can, I have a situation like this, and here's a simple example that some of you guys may have seen before. How many, raise your hand if you've seen ADMM before. I'm sure many of you have. Okay. So the high level idea is that if I have something, so if you take a look right here, if it wasn't for this constraint, you see how these two would be separable? And there's a linear constraint that links X and Z together. And so the high level idea is that imagine if I had F1 of S1 plus F2 of S2, subject to the constraint that S1 has to equal S2. Then it turns out that there's a clever way that I can build a penalized Lagrangian where I can do basically coordinate descent on each of those, and I'm guaranteed to converge to the optimal solution. And so I won't go through many details of that, but remember we have a quadratic, and then we have a, basically 3 terms. The quadratic term, negative log of Q, and negative log det. By the way, theta is basically just 1 over tau. So I multiply both sides by 1 over tau. And if I introduce the appropriate auxiliary random variables, where this is basically the weight, this is basically the determinant of the Jacobian, this is basically the transformation, and this basically represents the coefficients of the map themselves. If I do that, and I build the penalized Lagrangian, all sorts of cool stuff starts to happen. If I, so this becomes the penalized Lagrangian, sort of right here, and remember I still have the constraints that need to be obeyed. And keeping in mind, you guys, if I try to directly solve this problem, there's this positive definite constraint that becomes a pain. So remember I have my map, and it's a weighted combination of the polynomial functions, the polynomial chaos functions, and that weighted combination, my decision variable multiplied those functions, needs to be positive definite. That becomes very difficult in one fell swoop to solve, but because I generated this auxiliary random variable Z, I just have the constraint that it has to be positive definite. All sorts of cool things happen. And so I'll fast forward through this in just a minute. So with my auxiliary variables, I have the, so remember I had to penalize Lagrangian, but now I have to incorporate the constraints. So I add these terms here, plus the linear terms, the traces of the appropriate inequalities. And the beautiful thing that occurs is that when I go through the standard coordinated descent with ADMM, basically everything becomes a linear algebra closed form solution except one update equation. So it's either just standard matrix operations. I might need to find eigenvalue, eigenvector decomposition, and then there's only one point estimation problem that I need to solve. So remember I had n samples, and across each sample there's just one point estimation procedure I have to solve, which is just a d-dimensional point estimation algorithm. So basically developing a clever way to formulate this problem allows us to do this very efficiently. And so and the key thing we have to do is to solve one point estimation problem, which is done all the time with things like Apache Spark and all sorts of other algorithms. So we basically implemented the whole thing up in Amazon Web Services across all of our samples, a bunch of linear algebra updates and point estimation problems, each of which is guaranteed to be convex because of the log concavity of Q. And then from that, we basically get information about the whole distribution. So if we go back to Michael Jordan, in some sense, he basically said that if you're just doing point estimation, things are problematic. But by doing point estimation and by performing the appropriate linear algebra updates, we now can actually sample from the posterior so we can get the whole shape and all the uncertainty about the distribution. And so another nice thing about this approach is that we can actually use GPUs. And for some of the folks who care about these types of things, this just basically shows that when we use GPUs with multiple CPUs, then this is the amount of time to do a composition of 10 maps to compete, a competition in 10 maps. And this is the dimension of the, of the X's in the original space. And we can just see how the complexity grows. And you see, as you're allowed to use GPUs, the computation time sort of improves. And so just as an example, a result from the simulation, it's pretty self-explanatory, but I'm showing you the original samples and then how they're being, how they're converging to a Gaussian distribution. So it started off as basically a mixture of Gaussians, and you can see how just as I invoke each one of those compositions, how it's transforming them to this sort of Gaussian distribution. So this is almost like a computational Fulcrum equation. But the key difference is that I only have samples from P. and we're solving the sequence of optimization algorithms to do it. So what I thought I could do now is to share with you some results about how we go back to that set of problems that we looked at before. So I remember I gave you those three examples: Bayesian inference, active learning, and generative modeling. So within the context of Bayesian inference, for starters, I can pick a very controlled situation where I know exactly what the ground truth is. And so what I can see here is basically the IID samples from the prior, which in this case is a two-dimensional standard Gaussian. And then this is the posterior distribution. And one other thing that's nice about this approach with the transport map is, if people are familiar with something called 95% credibility intervals. So the high-level idea is that I know for this Gaussian, right, I can have this red circle which guarantees with 95% of the probability the points lie within here. Suppose now I want to get the 95% credibility interval, which is the analogous region of the posterior distribution. It turns out all I have to do is to take the points in the red and shove them through the map, and then those become that. And so I get the credibility interval for free if I have the associated interval for the prior. And also you see the acting upon each of the samples. Now within the context of Bayesian inference, again, this is just invoking my inner Michael Jordan. So I constructed a very specific situation where I have the blue curve and the green curve where the point estimate for both is the same. But I can show you that that we basically can extract more information. So this is just a standard logistic regression type of setting, right, where the probability of heads given your regressors is E to the transpose between the unknown coefficients and your regressors. So X is a pair of unknown coefficients and Y are your regressors. Okay, we know this very well. And so what I'm plotting to you here is here are our samples, right, our regressors, sort of right here. And so I can show you a situation where we have many regressors versus when we only have a few. Okay, and then I'm going to show you when I just solved the standard MAP estimation problem for logistic regression. Here's what I get right here, and as I mentioned before, what we get for free is that 95% credibility interval. Whereas here, so it's the same point, negative 3.9, 3.9, but here the credibility interval is wider. So this is the idea of providing uncertainty quantification. And so for our prior, something very nice like a Gaussian where I can get that, then once I build the transport map, I can just take that and it transforms it into these intervals. And this obeys common sense that as I get more data, the volume of this region gets smaller and smaller. But I can do this for an arbitrary data set as long as I can do so with the prior. So we also looked at something called the Boston housing data set, which some of you may be familiar with. It's a very, very standard data set that people apply a lot of their Bayesian inference algorithms on. And so we implement our transport map approach versus a Gibbs sampling type of approach. And basically what we see is that with our optimal transport approach with 25 compositions and 2,000 samples that we're training on, we're basically, if you take a look at the coefficients that we're getting and the error bars around them, we're basically getting the exact same thing as MCMC. And we know some of the challenges with MCMC is that, well, we can't always prove things about it depending upon the distribution we're trying to converge to. And further, there's this whole issue of the burn-in time, which we sometimes pick arbitrarily, whereas we don't sort of have that problem here. And this is a situation where I tried to communicate that more clearly. So remember I mentioned the Bayes risk, right? So I want to minimize this loss function. And so basically what I'm showcasing here is the trajectory of that expectation when I use our measure transport-based approach as compared to MCMC. And you can see for yourself this is superior. And so the high-level idea is that for a fixed number of samples, I get a better job of convergence as compared to MCMC. And so this is one potential sort of benefit of this. Now, another application that we got interested in is that a Ph.D. student in computer science named Justin Tentingblock, and he was interested in some of these applications of reinforcement learning that you can combine with Bayesian inference. And so the high-level idea is that there are some of these open source tools where you can simulate very complex dynamics of robots and other things. And what you would like to do is you'd like to learn a controller for these robots, but these are very, very complicated types of situations. So trying to solve like the HGV or something like that, HGV equations, is not necessarily obvious and has many degrees of freedom. But is there a way that we can have sort of a human in the loop where we basically have the algorithm take a sequence of actions and the human observes the actions that it took, and the human can basically say, this set of actions I prefer to those actions, and by time, with getting the human feedback, can you actually learn a control algorithm? And so we want to explore these types of ideas. So it's a human-in-the-loop reinforcement learning scheme. And so, as we know at a high level, I mean, you guys are in, well, some of you students are ORE students, so I know Jamal knows this. This is like standard Markov decision process. And so I have actions that are taking, I interact with the environment, and then the state of the system changes and a reward is provided back. And over time, suppose that the system does not know this probabilistic transformation, over time can it make decisions so that it optimizes the rewards that are taken. And so S of time t is the state of time t, AT is the action of time t, R is the reward at the time t for taking that particular state function. And so to go back to what I mentioned before, is a lot of situations for these algorithms, people sometimes define this reward function just by hand. And so what we wanted to do is in some sense to go a bit, this is also called reward hacking, and this can be an overcomplicated task, and we wanted to go sort of beyond this. And so we wanted to use this approach, as I mentioned before, called preference-based reward model learning. And so the high-level idea is that I'm going to build a parameterized reward function, and I'm going to let the weights of that reward function be guided by feedback that I get from a human being. And so some of you guys, have you guys heard of, does anyone know the professor named Peter Abeel at UC Berkeley? Does anyone know his name? He was Ph.D. at Stanford. So basically he got famous for in his Ph.D. that got him a job at Berkeley, is he basically showed how you could fly, you could have automated, completely automated algorithms that could fly helicopters upside down. And so what's interesting is not only what he did, but how he did it. And the way he went about doing it was having a human basically evaluate takes place. And by sequentially having a human basically showcase how it's done, over time, watching how the human does it, they basically try to infer the reward function and then solve an optimal control problem for the reward function that they learn. So we in some sense are trying to do something similar. In this case, the human is not showing us how to fly the remote control helicopter, but what we're doing is we're just going to actuate the robot, and we're going to do it, we're going to have pairs of trajectories. So the human's going to see pairs of state action pairs, and we want him to tell us which one he thinks is better. Humans are really good at saying, I like this one better than that one, etc. And so, so the first thing we do is that we have a set of basis functions for the state action pairs, and we have these unknown coefficients theta. And so those are like the unknown parameters in Bayesian inference that we want to learn. And it's basically a setup like this, and I'll explain this diagram in a bit more detail, is that I have a pair of trajectories or demonstrations that our algorithm shows. So sequence of state action pairs, a pair of them. And then what we do is we showcase it to the human being, and so they provide a preference, you know, 1 if they like the first one better, 0 if they like vice versa. And what we're going to do over time is we're going to build an estimate of the coefficients of that reward function, for which the high-level idea is that the reward function under the one that was preferred should be greater than the one under which it was not preferred. And so can we infer this over time as the human gives us more and more rankings, and then we can estimate the reward function. And so as I mentioned before, we're going to use our maps to do Bayesian inference to transform samples from our prior to samples from our posterior distribution, given the information from the human being that we got. And so what type of likelihood function do we use? Well, remember the human being is going to give us basically 1 or 2, 1 if they think that person 1 did it right, 2 if the other person did it right. But keep in mind that if I think that, if I like trajectory 1 better than trajectory 2, then it should be the case that the reward function under trajectory 1 is bigger than the reward function under trajectory 2 and vice versa. So we basically built a very simple model that the probability you declare 1, I'm just going to take the exponentiation of the sum of the reward functions divided by the sum of those two. And here I'm using trajectory 1, whereas in the other case I'm going to have trajectory 2 in the numerator. So what that means is that if you know, it's a coin flip, but both of the trajectories are the same, and as one is much more likely than the other, that means one significantly exceeds the other. What's also nice about this is that this is a log concave, and the sigmoid is log concave. So this P of y given theta model is nice and log concave. So that means that all our algorithms are convex. And so this is the high-level picture of what's taking place. And what we want to do is we want to use optimal transport to basically transform samples from the posterior. And what we're going to do is once we get samples from the posterior, that is going to dictate the new set of trajectories that we solve, because we'll just solve the optimal control problem associated with the reward function parameterized by those theta that we got. And so that's basically what I see right here. And so we do that, and so just to give a sense of the dimension of the transport maps in this sort of setting, is that as I go from inverted pendulum to a double inverted pendulum to this hopper based system, you're going from 26 to 61 to 71 dimensions. And what I'll showcase to you guys is for the untrained model, if you just apply something arbitrary, then as you can imagine, the inverted pendulum is going to be unstable. Likewise for the doubly inverted pendulum, and likewise for this system called hopper. So it's just going to fall over. I didn't show it more, but it'll fall over. So, so we use this, as I mentioned before, we're going to use this proximal policy optimization as our learning agent, and there's a 2017 archive preprint about this. And so, again, so I think this actually goes in a bit more detail. Let's see if this shows one where it actually falls over. And so, what I'm showing you here is, this is the untrained algorithm. This is the vanilla version of proximal policy optimization. And this is when we use or work with optimal transport and Bayesian inference. And you can see we're stabilizing this inverted pendulum a lot better. Likewise with the doubly inverted pendulum. Here is the untrained approach where it's about to fall over. When we use vanilla PPO, it does a little bit better, but I think it falls over at the end. If we watch carefully, it'll eventually fall over. And when we use our transport approach, it's a lot more stable. And then lastly, the most complex system is the hopper. And for the untrained algorithm, we see it's about to fall. With the vanilla PPO, you see it's beginning to bounce. And when we use our PPO with optimal transport, it's much more stable and bouncing around. So this, just tries to provide a visual explanation of how these algorithms tied to Bayesian inference can be used. So what I could do next is explain how we can use this principle of domain adaptation tied with optimal transport. And this should be sort of very simple. And so one of the things I've been interested in when I started my career at the University of Illinois is brain-computer interfaces. So the high-level idea is, suppose I put the shower cap over your head, and I basically allow you to either imagine left or imagine right. It's well known in our brain that basically the pattern of electrical activity in our motor cortex, it's called a homunculus. So basically when I am trying to move my left hand, there's a pattern of neurons that fire here, different pattern of neurons when I move this hand. And so actually when you just measure from the scalp, there are ways that you can decode that information. And you can already see that clear. You can see this pattern of voltage activity on the surface of the scalp differs, and as you see, it's a bit symmetric when you imagine left versus imagine right. And so this allows us to, in principle, do things like control with binary commands and whatnot. So the problem that we got interested in is, suppose I don't want to use the full shower cap. I want to use a technology that, for example, our research group developed, where you can just place these forehead stickers right over the head, and it's just like a piece of an adhesive that you, like a Band-Aid, you mount on your forehead, and it has 4 sensors right here, and we can capture electrical activity right here. Now the challenge is that if you take a look at the best algorithms for brain-machine interfaces that can disambiguate this, they like to use activity that's back here where there's a lot of hair in the back part of your head. But notice we have these forehead stickers that are already here. So we have good classifiers that can operate on the electrodes that are back here, but we're only measuring here. So I think you see where I'm going with this. Can I build a transport map that can transform samples from here to samples from here and then apply a classifier here? So if I only use these frontal electrodes right here, the takeaway lesson is that if I try to train a classification algorithm to do that, here's a standard ROC curve, and the area under the curve is 0.63, not much better from chance. Now, so if I use the back of the head, so the high-level idea is that the forehead is unobtrusive but bad performance, or I could use the back of the head, which is obtrusive but good performance. And you see here I get an area of the curve of 0.82, and so these are these electrodes C3 and C4, which are around right here and right here. And so, can I attempt to get the best of both worlds, or can I at least get somewhere between 0.63 and 0.82 only using electrodes on the forehead? And the high-level idea, what we do is we get the electrodes from the front, and we learn a transport map that transforms them to samples that look like they came from here, and then we feed this into a classification algorithm that's already been trained, and there are a gazillion of these in the literature, and when we do that, indeed, we do get a performance improvement. Do we get as good as being back here? Obviously no, but do we improve upon trying to just use stuff from here? Yes, we do. We get, about halfway between 0.75. So this allows you to get a sense of the area of domain adaptation, and people have used optimal transport principles, because if I have a well understanding when it's in this configuration, but now I have samples that are not in this configuration, rather than trying to learn to discriminate here, can I transform into here and then apply that knowledge there? That's the high level idea.
Quick question.
Yes, sir.
Can you go back a slide?
Yeah.
Can you somehow do both of these simultaneously?
Elaborate.
So it seems like you're building maps, then you're doing classification.
Right.
Can you do them together in a framework that?
So I think what you're saying is that from, it's like the data processing inequality or something. In principle, if you built a black box that just went from red right to green, in principle, yes, but the high level idea is doing that is in some sense kind of hard. Why not take advantage of all this knowledge? Because what underlies here we know makes sense, right? Almost from the neurobiology, and so can we transform samples from here to here? And so here's one thing I'll say. I don't have a concrete answer for this. Technically, you should be able to do just as well, but this is one of these things where we see in practice this idea of transforming samples from one space to a space from which we know how to look at things better. That intermediate step seems to be very beneficial in many signal processing applications. It's not necessarily optimal, et cetera, but practically speaking. So, so if you guys notice, I started off in the theory world and all this stuff, but now what I'm trying to do is I'm trying to connect the theory to practitioners and why they may want to use this. So that's what this represents. Now the last topic I tried to say, quote unquote, the best for last, is how many people here have heard of Gans, Generative Adversarial Networks? I'm sure almost everyone, right? So this is a very hot topic in machine learning. And I'm being recorded, so I'll be careful of what I say, because it's very, very exciting, but what we know about these neural networks is we can't always prove things about understanding exactly how they work, right? Because arbitrarily, so for multiple reasons, right? I would say the main reason is because when you do fitting for these algorithms, right, you're using stochastic gradient descent, but that's a fundamentally non-convex sort of structure that you're minimizing, and so you cannot always guarantee that what you're fitting, you can't always make guarantees about that. So there's lots of questions that we don't know, and so what I got interested about this generative modeling framework is that it appears as if it's very attractive to use the framework that we developed. And so the high level idea is I have these IID samples from P, and remember P could be very, very complex. This could be like the set of natural images or something like this. What's the, if I were to take every pixel in that image, it has an RGB value, right? So that's an R3. But then if I have, M rows and columns, and that's 3 times M times N, I mean R3MN, right? And I could treat those as just real numbers. What is the distribution of that over the space of natural images? It's very, very nonlinear and weirdly shaped. Suppose I could transform that to a standard normal in R3MN. What if I could do that? And so the high level idea is that if I can push the data to a standard Gaussian, then what I can do is I can just generate IID samples from a Gaussian, shove them through the inverse map, and now I have samples from the set of natural images, as an example. Is that sort of clear to everyone? And remember, with our framework, what we're fortunate about is because we built upon all that optimal transport stuff, we guarantee invertibility. Every infinitesimal map is invertible. That means the composition is invertible, so that means the inverse is also exists. So here's the takeaway, here's the punchline, here's what we're very proud of, is that, so we got the MNIST data set, which is in many deep learning papers on Gans. And so basically what happens is you're given a bunch of IID samples of handwritten 1s, handwritten 2s, handwritten 3s, and handwritten 4s. So that we then basically applied our machinery to learn a map. So notice that we're in 784 dimensions because they're black and white. So every pixel is a real number. And we have 12 rows and 12 columns, so we're in R784. And so we, this is what the original set of images from the MNIST data set looks like. Then we generated IID sample, IID Gaussians in R784, shoved them through the inverse map, and here are the images that we got. And and so they look like handwritten digits. So we're very excited about this, and so this is in our most recent sort of paper. And so, well, the takeaway lesson about this is that what we like about this is that you can make statements about the complexity. Obviously, it's linear the number of samples because we're just on empirical risk minimization algorithm. It's backwards compatible with point estimation algorithms because everything is either linear algebra or you solve one standard point estimation algorithm. What I like about it, what's cool, is that it makes these interesting connections between solution methods for computational fluid mechanics, non-equilibrium thermodynamics, and convex optimization, and there are many types of applications that you can explore with this. So with that, I sort of conclude my talk, and I like to finish with something philosophical. And so one sort of philosophical approach that guides how we think about our research is sort of the red ocean, blue ocean, right? And so if you think about the red ocean, that's where there's a lot of cutthroat competition in existing industries. So everyone's trying to stab each other, elbow each other out the way. And so it makes the ocean bloody red, it makes it painful, not fun to navigate. And if you can find yourself a blue ocean opportunity where there's a lot of unexplored areas, untainted by competition, and there's huge opportunities for deep growth, but more importantly, it gives you a sandbox to play in where you can play slowly and carefully and think carefully and not have to worry about hitting Google Scholar every moment that someone might have taken your idea. So with that, I conclude my talk. Thank you.
Question?
Do you have tasks where you're able to split the possible Q distribution parameterizations across many different pieces of hardware?
So I think what you're saying is if Q is in many dimensions, can you put some dimensions in one piece of hardware, other dimensions in another? Is that kind of what you mean?
Or different bases of the chaos decomposition?
The way, so, excellent question. So if you know a little bit about polynomial chaos, you know that the complexity explodes. You use a higher normal polynomials. Is anyone familiar with this, right? Especially if I'm at higher dimensions, right? Because that basically is a tensor product, and so these things can really sort of blow up. So a couple things I'll say. First of all, because we're doing the sequential compositions, where each one is kind of infinitesimal, you can actually get away with only a second or a third order polynomial chaos. Because remember, we're composing all of these. So we're ultimately building an extremely nonlinear map. But the learning process of going from rho k to rho k plus 1, you don't need that much nonlinearity, right? So that's one point. What we did is we distributed the samples, like x1, x2, we distributed those across. Remember, there's n samples, each of which is in d-dimensional Euclidean space. So what I do is, across the architecture, if I have n samples, I just put one sample on one, another on another. So each one of those is just a d-dimensional Euclidean space optimization algorithm. And then remember, it's all closed form linear algebra, one optimization algorithm, and then we just have iterative updates where we combine updates. And as we do this iteratively, we're guaranteed to converge. So that is a consequence of how we formulated it. There are many, it's like once you turn it, so it's one of those statements like all convex optimization problems are not created equal, right? So although it's convex and that means nice things, the devil's in the details of how you solve it. This is our approach. There could be many others.
Going back to the connection with your fields work,
Yes.
it's been a while since I looked at this helicopter stuff, but
Which he's not doing anymore, but I think it's such a beautiful philosophical way to explain not only that what I'm doing is cool, but it's really about how I'm doing it, and that's the takeaway lesson for the end.
so he was doing inverse reinforcement learning. if I
Correct.
remember, right? So he was given a solution that the human thinks is optimal and was learning what they were minimizing.
Exactly. It's exactly an inverse optimal control problem in some
And
sense.
here you're given two things that may not be optimal, but they're ranked somehow.
Exactly.
So are you learning the same cost as he was?
It's, I guess the difference is that in Peter and Bill's setting, it's so beautiful philosophically, right? But The high-level idea is if I have a bunch of expert pilots, what I could do is I could take their state action pairs, and from their state action pairs, try to figure out what is the policy. Because we know an optimal policy, right, from MVP is a deterministic mapping from a state to an action. But when we collect data, there's always going to be noise. So if you try to directly learn the policy, that policy in general can be extremely nonlinear, and so you don't learn well. So when you try to learn the policy directly, you train these algorithms, the computers always crash. Instead, what he did is he said, well, you know what? Rather than trying to learn the policy, let me learn the cost function they're minimizing, and across different experts, maybe that's more robust, and it's not as quote-unquote nonlinear, etc. And so indeed, when he did that, when he went through that inverse, that ended up being much more robust. So it's really making sure you know what you're looking for. In some sense, when there's no noise, they're equivalent, right? Policy relates to the reward function relates to the policy, to Bellman's equations, everything is nice, but all men are created equal, but not really, right? The reward function is the right way to think about it. So in our setting, what we got interested in is we're not having people control the robot for us. What we're having people do is we're showing people the trajectory. Another way to look at it is I had a graduate student, he had this nice analogy of what's called Monday morning quarterback learning. That's another way to think about it. So anyone here who's a football fan, you get really pissed off when your team lost and you said, well, you know what? They shouldn't have done that. I got mad at what they did. They should have done something different. So it's not as if you're saying what should have been done, you're just saying, I'm not happy with this. And so if I have two different sequences of state action pairs, the person is just giving a binary preference on which one they think is better. And then the idea is that over time, sequentially, after you keep doing this, assuming that your reward function should get better and better, now they're comparing better and better sequences of state action pairs, and ultimately that posterior distribution over the reward function should contract to a point mass over the true reward function. That's the high-level idea. The devil's in the details. But as you can see, it kind of worked, right? So that's the difference, right? They're giving binary comparisons, right? The high-level idea is to make this compatible with something a human feels good about doing. Humans like making binary comparisons.
Any other questions?
It's like voting, right? We only Democrats or Republicans. That's a topic we can have offline, right?
All right, let's thank Todd again.